Hey everybody, I just wanted to give us a short video on this chapter 4 material regarding our motivation for studying groups. Sorry for sounding a little congested, but hopefully you'll forgive me for that. So basically the idea is thus far we have introduced the concept of groups as being some collection of actions that satisfied a certain number of properties. And then we started to explore what things were groups and were not groups. And now we really need to understand why we would want to care about a group. And this is something that's typically lost in abstraction, right? Somehow you'll hear mathematicians wax poetic about the need for abstraction and the beauty of abstraction, and then often one forgets to ever provide convincing reasons as to what one gains from it. And so the idea here is we're going to see that this abstraction that we've been doing allows us to consider a lot of different things. And the idea then is by knowing something about a very small number of objects, in particular groups, then all of the things that fit in to the structure of groups will inherit all the properties that we know about the original one we studied. So in some sense we're hitting, let's say, 12 birds with one stone, in the sense by studying one particular group and then finding all the groups that are isomorphic or similar to it. And then we'll be able to actually pass along whatever information that we discovered in the first group to all the rest of them. So this is so basically we've introduced all these things. So what I want to do now is discuss practical applications. And now practical is of course a baited word, because these are not necessarily practical in the sense that you'll be walking on the street and somehow come across these things, but more so that these are things that we can physically envision, I guess I should say. And so we're going to pick some things from science and art and math, and the idea is we may think we would never want to study them, and that's perfectly fine. The goal here is to understand how we layer on our abstraction and then use it to study the objects at hand. So intuitively the idea is something is symmetric whenever it looks the same from more than one point of view. In a very loose sense, this really boils down to thinking if you can rotate the object, but rotation is not always exactly what you need to think of. But this is a very good thing to keep in mind. Objects that can be rotated, and if I don't move my point of view but end up seeing the same picture after doing various rotations, then we have that this object, let's say, exhibits some form of symmetry. And all the groups that we've studied thus far have these kinds of symmetry. So, and that's because all the things that we've dealt with so far are dealing with arrangements of similar things, and thus, let's say, doing rotations really boil down to doing rearrangements. And what this is going to lead to later is the fact that every group can be viewed as a collection of ways to rearrange some set of things. So this might sound like a strange theorem, and we'll get to it later, but the idea is pretty simple. When we're studying groups, when it boils down to the most basic way of thinking about it, everything that is a group is simply a collection of ways, meaning actions, so to speak, that allow you to rearrange some set of things. All right? And so what you can think of is, for instance, when you think to the integers modulo n, then this is somehow a set of things which are numbers. And by adding numbers, we're simply kind of rotating them, in the sense that if we glue them into a circle, addition can be thought of as rotating my dial, so to speak, counterclockwise. And in that way, we're rearranging from the original set to the new set. So then, of course, we want to understand how we could make a group from some given set or, let's say, list of symmetries. So we had an algorithm in the notes that made it pretty simple. The idea is we should identify all the parts of the object that are similar. Now, this can be a pretty complicated process, but what you should have in mind is the idea that when, for instance, we were dealing with rectangles or squares or triangles, we simply labeled the corners because all of the corners had some structures that were similar, in the sense they were 90-degree angles or 120-degree angles depending on the shape. So we identify all of them that are similar and we label them. And then you might say, but what if there's some important feature of it that is not similar to anything else? Well, then that feature will not contribute to the symmetry of this object. Basically, it will dictate what is not symmetric. So what you can think of is if you have something sticking out of the top, then of course rotating it 180 degrees vertically would make it stick out of the bottom. So it doesn't contribute to the symmetry, but it does dictate what is not symmetric. So then once we've labeled, we want to consider all the actions that rearrange the numbered parts but leave the object in the same physical space. Now, here what you should be thinking of is the square or the triangle or the rectangle, in the sense that when we manipulated them. However, it was sitting on the table when we originally started the problem, meaning if we had somehow the short side was here and the long side was on top, then whenever we manipulate this rectangle, it still needs to be long side on top and short side on the side, even if it means that the numbers have moved, right? So we have to somehow think about, we have something that fits inside of a peg, or let's say a hole, so to speak, and we pull that peg out, we manipulate it, but we have to be able to place it back down into the same hole. And then of course, if you want to visualize the group, we should go through and create our Cayley diagrams, just like we did in the previous chapter. So, now this is something we don't use in the actual notes, but we're going to refer to the physical space that an object occupies as its footprint. And so the idea then is whatever footprint it starts out in, we need to guarantee that whatever manipulations we do will preserve that footprint. All right. So step one is to number the object's parts so that we can track the manipulations. Right. That's the key with the numbering, is to realize what changes we've made. And then each state is simply a rearrangement of the object's similar parts. All right. So not every rearrangement is valid, and we've talked about this a lot. So you have to maintain the object's physical integrity and preserve its footprint. So for instance, back to the rectangle example, you can't cut the rectangle in half and then shuffle it around and then put it back together differently. Just in the same way, we can't rip off arms of a starfish and glue them back in a different place. Somehow we cannot break the original object, and we also have to preserve its original orientation or footprint. So, step two is asking us to find all actions that preserve this footprint and not just the generators. And so this is another place I think we've studied or struggled with as a group. So the generators are somehow the minimum number of things that you need to describe all possibilities. However, in step two, we're looking to really just describe all possibilities. All right, so when we want to go back and draw the Cayley diagram, one will reduce their consideration to the generators, but we still need to have knowledge of all possibilities. All right? And of course, when we're selecting the generators, you obviously want to try and select as small of a set as possible. So the idea is you can never have too many generators, but you can have too few. All right? And the idea is, what some of you have realized in your drawings, is when you have extra information, it only causes extra clutter. So once again, generators, you can be thinking of it as like a basis for a vector space, or let's say a spanning set for a vector space. A spanning set means that we have enough information to completely describe everything in my vector space, as long as I do linear combinations. However, a basis for the vector space is exactly the right amount of information. So what's the difference? Well, in terms of being able to describe things, there are no difference. I can describe everything that I want. However, when I have a spanning set that is not a basis, I have extra information that complicates my math and complicates my representations. However, by having a basis, I'm guaranteed that I am representing things in the most concise and nice way that I possibly can. So this is kind of our goal here. Not only do we want to understand everything that we can consider, but we want to be able to describe it in a very succinct fashion. And that's what you're needing to do if you're drawing the Cayley diagram. So, a first example that we're going to look at is to study the shapes of molecules. All right. So, for those of you who know about chemistry, obviously the shape of a physical or of a particular molecule can impact their behaviors. For instance, you can have the same exact set of atoms, but if you rearrange them in different ways, you get drastically different behaviors. Even for the same exact molecule, you have different isomers that have different physical and chemical properties depending on the actual, let's say, bending or type of bondings that we observe. So, for a simple example, we're going to look at boric acid. And so the idea then is, of course, we have this boron atom in the center. These blues are the oxygens and the greens are the hydrogens. And the idea is pretty simple. So following the definitions in 4.1, find the group that describes the symmetry of the molecule and draw a Cayley diagram. So we need to understand every possible rearrangement of this molecule that is valid. So for instance, in the notes, what we said was, or let's say first, before we get that far ahead, we're going to number this. So for instance, I'm going to call this 1, 2, and 3. And you might say, how did we find this out? Well, each of these little legs are similar, so I'm just arbitrarily giving them numbers. There's no need to give the red part a number. I mean, I guess we could, but the idea is any of our manipulations will not disturb the placement of this red atom. Next, we need to figure out all the valid moves that preserve the footprint of this molecule. So for instance, flipping the molecule, meaning if I were to pick it up on this end and rotate it over, would not preserve the current footprint, because the current footprint has one leg off to the left and the other is over here, whereas if I perform the flip that I've mentioned, it would put this one leg over on the right. So the only valid moves are actually 120-degree rotations, because a 120-degree rotation will take this green dot to this green dot, this green dot to this green dot, and this green dot to this green dot. So these 120-degree rotations are what is valid. So of course we can go whichever direction we want, so I'll choose clockwise. And this gives us exactly 3 actions: the do nothing action, my rotation, and a second rotation. Now, a third rotation is always valid. However, that move, in terms of its net outcome or net result, will be equivalent to the do nothing action. So one could write the relationship, for instance, E equals R cubed, but we won't include it because we don't actually gain anything from this. So this molecule is actually the same thing as our cyclic group C3. All right, and we'll discuss this more later, but the idea is pretty much each action is just simply rotations, and after we do 3 rotations, we'll end up back at the beginning. So we have now completely described the symmetries of this molecule in a group theoretical fashion, and this is kind of what the goal is right now, to determine what the group structure of some physical object is. All right. Now, once again, you might say, why would we care? Well, now that I know this molecule has a Cayley diagram like this, any other molecule that has Cayley diagrams like this will have similar properties, and I'll be able to just kind of, let's say, knowing something about one will allow me layering on knowing something about all of them. And that's really the goal, is to do these broad classifications that make our lives easier. Now, with this, what you may have learned in chemistry is that these molecules can combine in very symmetric fashions, and when they do this, they can typically rearrange themselves into something called crystals, which are these very regular ways of forming lattices. So what you can imagine is a crystal is simply taking this box, putting it beside it, above it, to the left, bottom, forward, back, and continuing in that way. So basically we end up with a bigger cube built from the pieces of these smaller cubes. And so, and the idea is chemists typically assume that, sorry, I'm still not feeling well, that's why I'm coughing. The chemists typically assume that this stretches on to infinity, and anything that still sits inside this infinite giant cube is a valid manipulation. So what does this do? This gives us a new, let's say, action that we can perform. Before, all we could do was rotate, flip, and things like that because it had to land back like this cube. However, when you have an infinite stretching of things, you can do translations. So what you can imagine is if we have the infinite number line just running across the page, and we put a bunch of tick marks, but we didn't label them, then if I take this number line and it's infinite, and I shift it over by 1 so that all the tick marks are still lined up, but I've actually shifted everything, then from my view, because of the nature of infiniteness, it's exactly the same. So I hope this makes sense, right? The idea is I somehow have something very long, everything's labeled exactly the same. If I pick it up and shift it by 1 unit, it'll still look exactly the same because as I go to infinity, I can't see any differences. There are no boundaries to consider. So crystals have that same kind of idea, except they have more than a one-dimensional structure. All right. So we're now going to talk about describing these infinite crystals, these crystals that actually can be defined in terms of infinite groups. Now, So to make our lives easy, rather than looking at this three-dimensional picture, we're going to look at this simple one-dimensional picture of something called a frieze pattern. And the idea is crystals are three-dimensional patterns. One-dimensional ones are called frieze patterns, and two-dimensionals are called wallpapers. So the group that describes all the symmetries of some infinitely repeating one-dimensional pattern is a frieze group. So for instance, what you should imagine here is this is simply a one-dimensional strip. And you might say, well, yeah, it has two dimensions because it has a thickness, but bear with me in the sense that there's a one direction of movement is what I mean here. And the idea is this stretches on for infinity. And so the idea then is an example of an action that would be valid would be to pick this up and move this diamond right here, which would move everything else in fashion, and all of the diamonds would line up on top of one another. So this translation to the right, for instance, by the appropriate scale, is a valid action because it preserves the footprint or the picture that I'm seeing right here. So, and it also has several other type of things, such as what is called a glide reflection. All right. So a glide reflection is simply, if we think of the following. If we were, instead of to take this diamond and move it all the way over, one could do a half move and then a flip. And by doing that, this would result in a picture that has the same exact footprint. So with that notion, a glide reflection, which is what I'm going to call this, is another valid action that we have due to the infiniteness of the group. So remember, when we have these finite pictures like a rectangle, they have boundaries, and when you move it left to right, it affects where the boundary sits. However, when you have something that's infinite in length, there's no such thing as a boundary, and as such, any movements in this fashion would not affect the endpoints, so to speak. And so the other thing to note is, of course, a simple vertical flip will not preserve the footprint because of why? Well, if I do a simple vertical flip, then I've changed the footprint or the structure. So we have some moves that are new and valid, but then we have some old moves that we liked that are no longer valid. So can we determine the group of symmetries for this frieze pattern and draw a Cayley diagram? Well, the answer is yes. Basically, all of your actions can be generated by two things: horizontal flips and glide reflections. All right. And you might say, well, what are all of our actions? Well, going back here, we have translations, we have glide reflections, and we have, really, that's about it, right? We can do horizontal flips, or I guess we should say we can do horizontal flips where if I flip about this point right here, it'll simply preserve the structure. So we have these, but no vertical flips or anything like that. However, it's the case that all we need to generate this is a horizontal flip and a glide reflection. And the idea is in this picture, glide reflections are in red and horizontal flips are in blue. And obviously we can't draw infinite, so we imply it with the dots. And the idea is a horizontal flip is its own inverse, which should be clear from the previous description, so there's no arrows here. And the glide reflections are not their own inverses. And what we need to remember is, if we go back here, we would have labeled everything. So this is a 1, a 2, a 3, a 4, a 5, a 6, a 7. Or if you really want, you can say this whole object is 1, this whole object is 2, this whole object is 3. And when we perform translations and things like that, we're moving from one number to the other. So remember, this is one way of talking about it, but when we're wanting to talk about glide reflections, the idea then is what we're going to do is we're going to shift and flip, and then shift and flip, and then shift and flip. And so in that way, we're just going to be labeling these tips of the diamonds as my numbers. And I'll validly move from here to here with a glide reflection, and then from here to here with a glide reflection. And this is what these red lines are indicating. All right. So there's a very complicated structure here, but what you should be imagining is I can glide reflect all the way down, and then performing a horizontal flip basically reverses the direction, and I'll keep gliding in this direction. So it's not somehow implying that my glide reflections are going differently. It's simply this. As I'm moving from left to right, if I define glide reflections to be right moving objects, then when I perform a horizontal flip, we basically take this thing up and we flip it. And so that means left to right becomes right to left. And so that's why we have this two-dimensionality look to it. And remember, this is just a choice of Cayley diagram. There are many other ways of representing a Cayley diagram that would have been perfectly valid. All right? So, now this is something that won't be terribly important, but this is kind of nice to know. The symmetry of any frieze pattern can be described by one of 7 different infinite groups. So no matter what kind of pictures you draw that have these infinite patterns, they're all equivalent to 7 possible things. And so the idea then is that means there's lots of frieze groups that are isomorphic or have the same Cayley diagram, or under this. I mean, they don't necessarily have the same Cayley diagram the way you've drawn it, but one can always draw them with the same Cayley diagram, even though the actual pattern you're looking at could be drastically different. So somehow group theory is only highlighting some bare bone structures, and this is kind of being very loose with our determinations here, but the idea is, imagine you line up, let's say, a group of healthy human beings. Even though they will all look drastically different from the outside, more than likely, on the inside, things start to look pretty similar in the sense they're built from the same building blocks. And let's say, even though these building blocks may be different in size, they're really the exact same in structure. So the idea is if one person has a femur and another person has a femur, they'll have different densities or different lengths or whatever else you want to say. However, they have a femur and it serves that same purpose, and one can envision that what we're doing in group theory is exactly that. We're digging down deep into the bones of these objects to determine exactly what is the core features of the problem at hand. So, if we had two-dimensional repeating patterns, they're called wallpapers, and there's actually 17 different wallpaper groups, and then there's 230 different crystal groups, meaning the three-dimensional repeating patterns. So it starts to get very complicated. But to give you an idea, loosely speaking, these are the only ways that we can see frieze patterns. And the idea is here, what you should see is something like this. The diamonds represent shapes that are symmetric in the sense that if I flip it up here, it looks like I just slid it up here. Does that make sense? The flips and the slides look exactly the same due to some symmetry of the shape. All right. And then let's say if I were to, and then the idea is flip, slide, rotate, right? I think you're getting my gist here. However, with these crescents, there is not this perfect symmetry, right? There's the ability that if I rotate or do particular manipulations, I might have a crescent that opens to the left and then all of a sudden have a crescent that opens to the right. So what this is implying is with your frieze patterns, if you have a picture that is either perfectly symmetric or somehow anti-symmetric, those are your only two options. Anything else that has a repeating pattern somehow reduces to this under enough of relabelings. So we can put them both on the bottom, which of course in your mind should mean that's equivalent to putting them on the top, because in a group I can simply perform a horizontal flip in this particular circumstance. Then we have the option where we offset them, right? This is the pattern we just looked at. This would be the equivalent pattern for these kind of anti-symmetric shapes. Then we can do something where we put them on top and the bottom matching up, and what you can see is for this guy, this is the only option. However, here we have two different ways of lining up these anti-symmetric shapes, and what you could do is convince yourself that there is no other rearrangements that you could do that would make any sense. So, of course, this opens up what I think are some natural questions. What are the basic types of symmetries do these frieze groups have? What are their generators? Which of these frieze patterns have isomorphic frieze groups, which is a fancy way of saying which ones are most likely to be equivalent to something else? And which of these are abelian? And this might not be a natural question to you, but the idea is in which of these is it exactly equivalent to, for instance, do a translation and then a glide, and then versus a glide then a translation. And all of these are natural questions because it tells you a lot about what we can do. For instance, this is a way off topic, but in Calculus 3, you learned from something called Clairaut's theorem that if you're taking partial derivatives, it doesn't matter whether you do the x first or the y first because you have this commutativity. However, that's because you were doing things in very flat land, so to speak. But if you wanted to take partial derivatives, for instance, on the surface of a sphere, the direction that you choose to go matters very much, right? In the same way that if you're standing near the edge of a cliff, the difference between going forward and then right, or going right then forward, is one of them may leave you on land and the other one may send you plummeting off the edge of the cliff. So this abelian question is very important because it means if it's abelian, I can do things in any order and I do not have to be careful when I build my group. However, if it's not abelian, then there is the need to be careful, and this is something that we need to understand. And let's say even if we haven't dealt with it much, there should be a question you always have in your mind, because if you need to build, you need to understand whether the order in which you perform your directions matters. All right. Now, just to let you know, here are the 17 types of wallpaper patterns. I don't expect you to internalize these or understand them. It's simply, if you're interested, this is a way to visualize them. However, there's also this equivalent fashion that is actually kind of more, let's say, endorsed by the Chemical Society. And in this one, you can see there's just exactly the same thing. It's just a different way of representing them. And you could spend some time trying to see how they relate if you want, but this is simply just a representation of them for your own edification. So, next we have this contra dancing, or square dancing, so to speak. And I think this is something that has raised questions for you guys, so I want to make sure that I'm very clear here about the way this works. So in square dancing, the way it works is you have a caller who is usually in the movies the, let's say, shortest, roundest man with the biggest, whitest mustache that's talking in a cowboy hat, telling them what to do. But in general, it's simply someone who is telling everyone how to move. And by doing so and telling everyone to move in the same fashion, we have this very globally aesthetic dance inside of the hall, right? So it's not just that each local pair is looking good. It's that as a whole entire group, everything looks good and works well, and there's no collisions and things like that because we have a structure. So each move results in starting in one position and ending up in another. And so in a sense, it doesn't matter how you move from one to the other as long as you perform the desired move. So we'll give them their names later, but that's not so important. Now, for the sake of clarity, let's say I am assuming that we have two heterosexual male and female couples. Of course, we can manipulate this in however we want. So what I want to say here is it has nothing to do with the actual engendered nouns that I'm choosing, other than the fact that it seems easier to do that rather than just labeling them person 1, 2, 3, and 4. All right? And then the idea is I will simply assume, just for the sake of simplicity, that one of the women is in the upper left, but it doesn't really matter if we choose something else. All right? So here are our moves, and so to describe them, what this is really saying is if you have a set of 4 people where I'm always drawing the woman in the upper left, but that doesn't mean that that has to be where she is always. Circle right is simply to move everybody to the right in terms of this structure. So what you can see is, of course, then we would have a man up here in the left corner, and that's fine. The idea is regardless of the original orientation, circle right simply does this movement. Ladies chain is saying, and this is kind of why it's important to know, let's say, to give them some kind of, it's not important, but let's say this is why we've chosen to give them some kind of engendered nouns, is the fact that when we perform ladies chain, this is saying regardless of where you are, the ladies should switch places. And this is actually set up in such a way that the ladies will never, for instance, be vertical from one another. This is never an option. So ladies chain will always be some kind of diagonal movement, either this diagonal or, in a different situation, this diagonal. Swing on side, you can think, is just men and women switch place. All right? But this is a swing on side in the sense of we've given it some kind of directionality. This side is meaning left to right in the way that I've drawn the picture. All right? And gents allemande is simply the same thing, which is just diagonal movement of the men. Right and left through is both simultaneous ladies chain and gents allemande. And the California twirl is somehow the kind of men and women of the opposite pairs switch positions. Now, before we move on, what you should really take from this is a pretty basic idea. This is a square. Pretend that this is a square. And let me label this position 1, 2, 3, and 4. Then circle right is nothing other than a 90-degree rotation of a square. Ladies' chain is nothing other than a particular diagonal flip of the square. Swing on side is a horizontal flip of a square. This is once again a different diagonal flip. And this is obviously not just a diagonal flip, but what you can convince yourself of is this is some, let's say, diagonal flip in one direction and then an additional diagonal flip in the other direction. And finally, this here would be equivalent to a vertical flip. So, if we want, we can envision this as just a square, hence the square dancing terminology. And from a group theoretical standpoint, there's nothing lost. It is exactly a square, and it has all the properties of our square group that we did in the previous chapter. So, now that we have this, we can ask ourselves, do the 6 actions generate a group? And the answer is yes. And why is that? Well, because we know that the square does. But even more than that, we have a list of 6 actions. That's clear. Every action is deterministic, assuming that no one breaks their ankle and quits. Then the idea is if you tell them to do ladies' chain, they will do ladies' chain, and that's the only outcome. Every action is reversible. How? Well, tell them to do ladies' chain again. Tell them to circle right 3 more times. You get the kind of picture. There's always a way to reverse what we've done. And every sequence of actions is an action in its own right. And what you can convince yourself of is no matter how many times I do these actions, I will not break this kind of structure, which is that I have kind of man, woman, man, woman, man, woman, man, woman. And that's really the structure that we have here. And of course, what you could say is, well, I'm wanting to envision the structure being that the woman has to be there. And you could do that, but in reality, what you should really be thinking is these are just people. And of course, no matter what I do, I'll simply have 4 people arranged in a square. So we have that every action is an action in its own right, in the sense that compositions of actions will not break the footprint or the structure of the original square. So this is just saying that we have that this is the same structure as the group of symmetries of a square. So I hope this clarifies some of the questions you guys have been having on the homework regarding how to consider these contra configurations. Now, this last one is more complicated and not something I'll ask you about, but is maybe slightly more interesting. Another area in which groups arise is the study of braids. Some of you probably have heard of this thing ubiquitously referred to as knot theory, and this is kind of along these lines. And what I mean is, I claim that somehow this is the best way to understand it in the sense that we can do these compositions of tying knots, so to speak, where tying a knot is simply crossing particular lines. But you would need to understand what I actually mean by any of these lines in order for it to make sense. So, keeping this in mind, and the notion that we would like to study the braid group maybe, if we were interested, and of course a braid is somehow multiple crossings is how you can view this. And the easiest way to think of it is as follows. So, imagine that we have 4 items lying on a table, and let's say each of these items are aligned in let's say 2 sets of 4 lines where each one's kind of lined. So what do I mean? Here are the 4 dots, and then similarly there's another pair of 4 dots across from them. And then we'll connect each 4 dots with a vertical line. Alright? And so what you can think of is each of these 4 strands creates this one-to-one correspondence, like a nice function like you draw in middle school. And such a connection is called a braid. Alright, so what do I mean by a braid? It's simply a connection of these 4 things, and the number of elements kind of dictates how many strings there are, and a braid is simply an arbitrary connection of them that follows some rules. So let's look at them in more detail. So for instance, the following 2 connections are braids, but they're different braids. Because why? This braid is going over the top, whereas it's going over the top coming this way. So if you'd like, you can always think about the origination point versus where it ends up. And this is kind of saying from the left it goes on top, or the first guy goes on top, whereas here it's saying from the right, from the left, the second guy goes on top. So these are different braids, but these are braids. And if they can be made to look the same by pulling the strands, then they are the same braid. So what do I mean? If I were to take this braid, so think of this top one right here, and I were to pull it under the third one and then over the fourth one, I haven't changed the connections, right? So what you can think of this as a function. It says it sends x1 to x2, it sends x2 to x1, it sends x3 to x3, x3 to x3. So these braids are the same because they describe the same kind of sending behavior, right? x1 still goes to x2, even though it took a funny path. All right. Now, we require that these braids move left to right, so something like this is not allowed. And you might say, well, it's still doing the left to right thing. That's true, but this is something that affects my ability to stretch it, and it breaks that. And the composition of two braids is pretty simple. Imagine taking these 4 dots and connecting them to these 4 dots, and then erasing the dots and just having this line that goes from here up to this dot, then we come over, and then it goes up. So the idea is x4 goes to x3, but this guy sends x3 to x2. So when we draw the composition, we just get x4 to x2. So braid composition works exactly like function composition in this framework. So these are braids. And as such, this means that all the things that we've built can be described in some very fundamental ways, which are basically there's the ability to switch positions or cross things. And the idea is there is some level of, let's say, commutativity here when done in conjunction with one another. And similarly, there's this funny looking relation here. And this relation here is once again kind of corresponding to the fact that if we do multiple kind of crossings in unison, they can be equivalent to another set of crossings. Now, and the idea is, of course, since I'm not going to ask you about this, I would simply say if interested, you should kind of look at these structures and convince yourself that basically any of these drawings that I've made right here can be done using some very simple ideas. And the idea is each of our actions look pretty simple. I would call this sigma 1 because it crosses 1 over the top. I would call sigma 2 the one that crosses 2 over the top of 3. And then I would call sigma 3 the one that crosses 3 over the top of 4. And then you might say sigma 1 inverse is crossing 1 under 2. Right, so we have these very clear ways of describing these. And these sigma 1, 2, and 3s are related to exactly that kind of notion. Except I have my numbering kind of backwards from what I've just said on the previous slide. So what we have are the following observations that, let's say, may or may not be interesting, is the set of braids on n strings forms a group. Why? Because no matter how many times I cross them or uncross them, I still have braids. The combination of braids is concatenation, meaning we kind of glue together these ends. And so this means that every sequence of actions will be an action in its own right. Every braid is reversible. Basically, you untie the shoestring you've just tied, loosely speaking. And this B4, which is the set of 4 horizontal lines with the 3 potential crossings, is the group that's simply described by, we need the following, that if I do 1 crosses 2, and then 2 crosses 3, 3 crosses 4, and then I do 3 crosses 4 versus 1 crosses 2, they have no effect on one another. Well, that makes sense. But if I cross 1 and 2, and then I cross 3 and 4, it doesn't really matter the order I do it. So this is what this relationship here is saying, and this is what this is trying to imply here. Somehow, since they don't cross or touch one another, there is no interdependence, so to speak. And similarly, we have this following idea. If I cross, for instance, 1 and 2, and then I cross 2 and 3, and then I cross 1 and 2, this would be equivalent to crossing 2 and 3, and then 1 and 2, and then 2 and 3 again. And this is something you have to kind of write down and convince yourself. Now, I'm not asking you to prove that this is true or anything like this, but I wanted to introduce it for several reasons. One, it's a very interesting group that is different and, let's say, slightly more exotic. And two, this here is what we could call a group presentation. This is a way of describing the group that is very much dependent on how we choose things. However, this group presentation is something that we will be studying more in the next chapter, so I thought it was nice to introduce this. So, Of course, email me if you have questions. I'll be working through the other emails I have from you guys. I realized there was at least one typo in these slides. With the braids, don't get too bogged down in this. This is not something that we're going to spend a ton of time on. This was simply an additional example that you could look at that you may or may not find interesting depending on whether or not you're looking for something that is more mathematical. So these braid groups have a lot more rich mathematics behind them, say, versus something like contra dancing. So they're simply included to give us an additional thing that we could be thinking about. All right. But if you do have questions about the braid group, you can still ask me, and I'll do my best to answer those questions as well as I can. All right. Thank you very much.